Namaste. Myself Nagaraj, working in the Department of Physics, Brodar Institute of Technology, Hospete. Today, I am going to discuss the aspects of semiconductivity. The conductivity of a semiconductor will be discussed. And the another aspect is what will be the Fermi level of a semiconductor. And the third one will be the famous phenomenon which was explained by the scientist Hall, known as Hall effect. When we want to discuss the conductivity of a semiconductor, here let us consider a semiconductor. Let an electron cover a volume per unit time, which is given in terms of area and its velocity as A into Vd, Vd being the drift velocity, A being the area of cross section of a semiconductor. If, say, for example, small n are the electrons present within the semiconductor, then they would be sweeping or covering a volume of NaVd. If small e is the charge on each electron, then the rate of flow of charges, or we can also call it as current, will be given by I equals to MEAVd. Also, we know the concept of the current density. J, by its definition, it is the current flowing per unit area of cross section. Current I is given by MEAVd by A. Hopefully, AA will get cancels with each other, left with NEVD. And also, we have learned one of the parameters associated with conductivity as the mobility of electrons. By the notation mu given as mu equals to Vd by E, Vd equals to mu into E, E being the applied electric field, Vd being the drift velocity. Now, upon substituting for Vd, I get back J equals to Ne mu into E. Hence, it can also be written in terms of conductivity sigma as J equals to Ne sigma. This is the another form of Ohm's law, which they say, and here the conductivity sigma equals to Ne mu. N the electron concentration, E the charge, mu the mobility of the particles. Say, for example, for a conductor, we do have only one kind of particles which accounts for the conductivity, that is electrons. Whereas in the case of semiconductors are concerned, two particles will share their part for the conductivity of a semiconductor. One, the electrons, and the other one is holes. And say, for example, if electrons are supporting or sharing their conductivity for a semiconductor, then what would be the conductivity due to the electrons? Let N be the electron concentration, mu E be the mobility of electrons, then the conductivity due to the electrons will be sigma E equals to Ne mu E. If, say, for example, if the holes are contributing for the conductivity of a semiconductor, then what will be the conductivity due to the holes will be given by sigma H equals to Pe mu H, where small p being the number of hole concentration, mu H being the mobility of holes. Then the total conductivity of a semiconductor will be the sum of conductivity due to the electrons and the holes. Substitute for sigma E and sigma H, and this is the general relation for the conductivity of a semiconductor. If I want to know for an intrinsic semiconductor, as intrinsic semiconductor says that number of holes will be equal to the number of electrons. For example, if I take the silicon or germanium, the purest of all the semiconductors which we know, they will have the valence as 4. So 4 number of electrons will be there, 4 number of holes will be there. Then such electron are the intrinsic carrier density will be taken as Ni. Substitute for N and P as Ni, take out Ni outside, hence it becomes sigma equals to Ni into E. Within a bracket, write it as mu E plus mu H. This is where Ni being the intrinsic charge carrier density. This is an expression for conductivity of an intrinsic semiconductor. Now, if I want to know what would be the Fermi level of an intrinsic semiconductor, sir, what is this Fermi level is? Fermi level, which is associated with the highest occupied energy level by an electron at 0 degree Kelvin. But which was explained by scientist Fermi. Okay, on his name we have the Fermi energy, and the energy level corresponding to the Fermi energy will be known as Fermi level. Right. So here we are only interested in obtaining for an intrinsic semiconductor. Now we have a straightforward relations for electron concentrations and hole concentrations. The electron concentration is given by 4 root 2 by h cube. Within a bracket we have pi me star kt whole to the power of 3 by 2 into e to the power of ef minus eg by kt, where me h being the Planck's constant, me is the effective mass of the electrons, k the Boltzmann constant, p the absolute temperature, and ef is the Fermi energy, and eg is the forbidden energy gap of a semiconductor, where we do classify the materials based on the energy gaps if they have. And accordingly, for the whole concentration, we have a straightforward relation as P equals to 4 root 2 by h cube, within a bracket again pi mh star kt whole to the power of 3 by 2 into e to the power of minus ef by kt, where mh star is the effective mass of the holes. And when we want to discuss for intrinsic semiconductor, we say that number of hole concentration must be equal to the electron concentration. So when I do so, when I equate n equals to p, fine. Upon equating these two equations, we get back taking this e power minus ef by kt to the LHS, we left with e power plus ef by kt, and several parameters gets cancelled. They're common in nature. One is 4 root 2 by h cube will get cancels, pi get cancels, kt get cancels, left with mh star by me star whole to the power of 3 by 2. And since the bases are same, add the powers. We left with e to the power of 2f minus eg by kt equals to mh star by me star whole to the power of 3 by 2. Now I am interested in obtaining the relation for ef, which is hidden within the exponential parameter. Now what I should do, I have to eliminate this e. In order to eliminate this e, I need to apply ln on both sides. Applying ln on both sides, we get this e gets eliminated, and this is equals to 3 by 2 ln mh star in divided by me star. Now rearranging the parameters, we finally get 2ef equals to eg plus 3 by 2 kt into ln mh star by me star. And once again, rearranging the parameters, ef equals to eg by 2 plus 3 by 4 kt ln mh star by me star. Now under practical conditions, as I mentioned, as I say, effective mass of the holes will be taken as effective mass of the electrons. If this is a condition applied to this equation, then these two will get cancels, left with ln 1. Ln 1, we know the value of ln 1 is 0. 0 into anything is 0. Hence we get back a relation like ef equals to eg by 2. This is an expression for Fermi level in terms of energy gap of an intrinsic semiconductor. And ef is Fermi level, eg is energy gap. So kindly do remember this relation, which is so helpful for us to calculate what would be the Fermi level of an intrinsic semiconductor if I know the energy gap of an intrinsic semiconductor. Now, next aspect is quite important, having a wider applications part, which was explained by the scientist Hall on his name, known as Hall effect or Hall phenomenon. Here it says, when a current flows in a semiconductor subjected to an applied magnetic field, then the electric field gets induced in a direction perpendicular to the current and applied magnetic field. This is the phenomenon is known as Hall effect. Now, when I have three such fingers which are mutually perpendicular, right? If the forefinger directs the direction of the current flowing, and the middle finger directs the direction of the magnetic field applied, then the electric field gets induced in a direction which is directed mutually perpendicular to these two, fine, towards the direction of the thumb, which is directing, having the direction of electric field that gets induced. So here what we do is we consider a semiconductor slab, okay, of length d and width as w, carrying a current I along x direction. It is of n-type material. N-type material usually have majority charge carriers as electrons. Electrons are more in number in the n-type of material. And magnetic field is applied along the z-axis. And as a result, they say that electric field gets induced along y-axis. Right. Now, whenever the electric field gets induced in the y-axis, it pushes all the electrons which are lying in the phase 1 towards phase 2. Usually, the electrons will be here at this stage. When the electric field gets induced, these electrons are pushed downwards and hence left with the holes. Whenever the electrons push downwards, there exists a potential drop. Fine, the potential difference. The potential difference between these two phases will be known as Hall voltage. Hall voltage, here it is mentioned. The potential difference between the two phases is known as Hall voltage, and the electric field is known as Hall field. And here the force that can be calculated with the help of two such parameters. One, the force due to the applied magnetic field, and the force due to the applied electric field. The force due to the electric field which gets induced, fine. Here it is Fe, it is mentioned. E stands for electric field. Small e into EH. Small e is the charge. Capital EH is the Hall field which has been generated. Similarly, the force due to the applied magnetic field is Fb equals to BeV. Capital B is the applied magnetic field, small e is the charge of an electron, and small b is the velocity with which they travel. And upon equating these two equations, we get back BeV equals to E into EH. And also we know we have defined electric field basically as the potential drop per unit length of a material. It is the potential here, it is VH, Hall voltage. The length of a material, semiconductor, it is d, small d. Hence it is VE. E is get cancels, left with VB equals to VH by D. VH, our intention is to obtain a relation for Hall voltage, VH. VH equals to VVD. Now, what I do is I take the relation for current flowing through material, either a semiconductor or a conductor. The current will be having a relation I equals to MEVA. So therefore, V equals to I by MEA. A is the area of a material. Here the area is length into breadth. Hence it is length is D, and the width which we have taken it is W. Substitute V equals to I divided by MEW into D. Let us call this as equation number 4, and this is equation number 3. So, sir, why it is needed to have a relation for V? We have to substitute in this equation 3 so that we get back final expression for VH. So, what I do is I substitute this V equals to I divided by MEW into D in the equation number 3. Upon substituting, I get back BDI divided by MEW into D, where small d's get cancels, and left with VH equals to DI by W into, I take out 1 by ME outside into 1 by ME, and I write this 1 by ME as RH. Hence, the Hall voltage expression will be written as VH equals to DI by W into RH. So, where VH is the Hall voltage and RH is being the Hall coefficient. This is an expression for Hall voltage in terms of Hall coefficient, having the parameters, the applied magnetic field, the current flowing through a semiconductor, and its width. Here the RH, the Hall coefficient, RH is given by RH equals to 1 by NE. Small n is the electron concentration, E being the charge of an electron. So this is an important relation to calculate what will be the value of Hall coefficient if I know the value of electron concentration. If I know the value of Hall coefficient, I can easily calculate what will be the potential difference between two phases of a semiconductor. Thank you.